Hello, students. Today we want to discuss some additional equations solving techniques that use the ideas that we've already formulated. That is, we don't have to worry about a brand new structure. We use what we've developed and then make a few adjustments to solve equations that have different forms, but not so different that they look unfamiliar. So there are three types of equations that we want to consider. One equation has radicals, and so we're going to look at techniques to remove radicals. The other type of equation will be that of quadratic form. We've studied how to solve quadratic equations. We've even looked at the imaginary unit and how we can actually adjust the square roots of negative numbers in the quadratic formula to get a valid solution. So that was a big plus. And then the last technique, which I think is probably the easiest, is where we just apply basic factoring techniques. That one's kind of a misnomer because we're always factoring when we work with equations, but a particular instance where we just see a convenience. Okay, you may see certain terms as you group them. A simple factoring technique will occur to you. So I can make this mention that as we work through these techniques, you will see these types of equations come up again and again. In this class, in pre-calculus, in the calculus sequence, they are very important fundamental techniques. So like I said before, lots of the strategies that we learn in this class, even though they appear to be very basic, they're fundamental. And as you get better and better at these, you'll find that your confidence in doing mathematics will certainly improve. So let me share my screen so we can work on some equations. Now, what I said before was basically we want to start with radicals and then move to quadratic form and then just basic factoring. But the interesting example that we're starting with is just a means of removing radicals. So when we actually remove a radical, we certainly can introduce solutions that don't necessarily work in the original equation. And so I'm going to write this up here. We would say extraneous solutions. The idea is we know of techniques to reduce the complexity of an equation that don't necessarily introduce extraneous solutions. But when we actually square both sides of an equation, the possibility is there. And so if we do that process, we can at least be comforted by the fact that we have an implicit equation, which is valid, but we always have to go back to the original equation and make sure that whatever solutions we have to that new equation actually solve the original equation. And we may find that some of them do not. So let me just remind you, as long as you're using the standard techniques that we've learned so far, the introduction of extraneous zeros does not occur, but the squaring process can certainly do that. So what I've written here is just maybe like a little rule of sorts. If we have u and v being real expressions, and letting n be a natural number, 1, 2, 3, 4, etc., the counting numbers. Then if we take the nth root of u and set it equal to v of x, we can think of that as being an explicit form, even though it may not actually have the form we care about. And then we can remove the radical by raising each side of the equation or each term to the power of n. Raising this side to the power of n will absorb the nth root, just leaving us with u of x, or the argument of the nth root. And then, of course, raising v to the nth power gives us this. So we can think of this as an implicit equation. It's kind of like working with arcs of a circle. We usually enjoy implicit equations when it comes to the conic sections like circles, ellipses, parabolas, things of that nature. But we will spend more time on those objects later in pre-calculus. So, as I've said here, the common occurrence that we see a lot in mathematics is when we have n equal to 2, or the so-called square root. And so you'll see many examples of this. And it doesn't mean that it's the only one. It just means that it's one that occurs commonly in mathematics. So what I want to do is a couple of examples that use this technique. So let's get started. I'll move this over just a little bit and adjust Professor Alice over here. There we go. So let's see, what are we going to start with? We've got the square root of x squared minus x minus 7 equals x plus 3. So now when we look at this, what we want to do is apply the rule here. That is, here we have n equal to 2. And so we want to move to this side, which means to raise each side to the power of 2. Now, you don't have to explicitly write raising this to the second power. You can just write the argument if you wish. So now we apply the rule. So we get x squared minus x minus 7 equals x plus 3, but now, as we have over here, this is raised to the second power. So we go from here to here, again, relieving the square root on the left-hand side, and then adding the power of 2, or the square, on the right-hand side. Now we have an equation that is free of radicals. So basically, this technique provides us with an equation that fits patterns we already understand. And so we can use those techniques to solve and then check to see if what we actually find for x, if indeed we do, works. So equivalently, now we can look here. Let's go ahead and expand the right-hand side. So we get x squared, again, 3x times 2. Again, we like that perfect square formula that we used when we complete the squares. So that's really indispensable. Very useful. So again, never forget the middle term. Remember, you take the product of the x and the 3 and multiply by 2, just like we were doing when we were considering completing the square. So that formula is very useful to us. Now, we see what's very interesting here is that the x squared terms absorb. They're just on opposite sides of the equation. So these are no longer in the picture. They're hanging out, but they're zero, so they don't impact the equation in a tangible way. So now, equivalently, we have negative x minus 7 equals 6x plus a 9. Now, at this point, if you like, we can just go ahead and remove everything to one side and then factor it using zero product, since it's very simple. So this will give us a 0 when we add x to both sides. So x plus 6x is 7x. And then when we add 7 to both sides, 7 plus 9 is a 16. But of course, now we can use the factoring technique. Just factor a 7 from both of these terms. So we have a 7 times an x plus 16 over 7. So this is the square, this is using the eliminating of the square. I was going to say square root property, but that's not quite what we're doing. We eliminated the square root, but now we're going to use the zero product. So again, zero product. We see this works really well with the quadratics as we set each factor to 0. And so even in the simple linear case, we can see now that this will be 0 when we set this factor to 0. And that clearly gives us x equals the additive inverse of 16 over 7. So equivalently, x equals negative 16 over 7. Now, again, in some cases, checking zeros is really simple. But of course, when we get fractions, we're going to have to work a little bit harder. So let's just go ahead and check this, since we did have to square to get this value of x. So let me move this over just a little bit. Good. So now I can move this way and not be out of the picture. Excellent. Okay, so let's just do a quick check. Now, don't worry about writing the radical. Let's just do the x squared. So we're going to say x equals negative 16 over 7. In some cases, it's a little bit longer. Most cases, it's really quick. So this one's just a good practice with some fractions. So now we're going to square. So we're going to get negative 16 over 7 squared, and then minus x. So that would be plus a 16 over 7. And then we have minus a 7. So we just want to see what that would equal. And then, of course, we can check the right-hand side. But I'm just looking at the argument of the square root, and then we can square root it later. So now we have a common denominator of 49 when we square the 7. And of course, negative 16 squared is 256. That's a perfect square we remember from general math. And then, of course, we have plus a 7 times a 16. And then, of course, a minus 7 times a 49, just getting a common denominator. So this is just simple fractional arithmetic, but useful. So now we'll multiply 256 plus, and then, of course, the 7 times a 2, that's a 42 with a 4. So that's a 112. And then, of course, 7 times the 49, that gives us the 343. Again, these are powers and products that we use quite a bit. Divided by 49. So now when we add these, we get an 8, and then we get a 6, and then a 3, minus 343 over 49. And now, of course, the 3 from the 8 is a 5. And of course, the 4 from the 6 is a 2. And so we do get a perfect square. So now the left-hand side is just the principal square root of 25 over 49, which is 7. Excuse me. I'm thinking of the denominator first, which is 5 over 7. Okay, so now let's look at the other side. We have, let's see, x plus 3. So in this case, negative 16 over 7 plus 3. So let's just write the 3 with a denominator of 7. So we have negative 16 over 7 plus 21 over 7. 7 times 3 is 21. And of course, the difference between 16 and 21 is 5. So that side was easy. So we see that when we check, we get valid. So this is a check for us. Usually the check is a little bit more straightforward with it than this, but you can see, since we have a quadratic here and we get a fraction here, then there's going to be a little extra work. But now we can say we have a verified solution. Just remember, I don't usually check solutions when we don't have the problem of extraneous. When we've done techniques that don't introduce extraneous or have the possibility of introducing extraneous, we usually don't check. What we do is make sure that our techniques were good. But this process does not do the check for us. That is, once we find the value of x, we need to verify it. Okay. So let's look at another one just to get some practice. And in your homework or in your lecture notes, there's a nice one here that has 2 radicals in it. So let's look at it. So usually what we're doing is solving this in the real numbers. And then, of course, if we're dealing with polynomials, we can sometimes look at the imaginary zeros just because we know how to deal with them. But when you're solving a problem especially in your homework, if they only ask for the real solutions, then you're off the hook. If you know the imaginary ones, you're just not asked to provide them. So always answer the question. But if you know the additional information, just kind of do it to the side as additional practice. So we have the square root of 3x plus 1 minus the square root of x minus 1 equals 2. And again, we want to solve the equation, just like in the last one. So when we think about this, and this is completely up to you, there's no special way to do this. Since we have two radicals, you're thinking, well, you know, we could square this side, eliminate that radical, and then on the middle term have the product of the two radicals. And that would be a way to do it, but it gets a little bit complicated. It's not a bad way to do it. It certainly works. But usually the first time you do this, it might be easier just to isolate one of the square roots and then square, isolate the last one and square again. But I'll leave that up to you. So let me just provide the example of isolating one of the square roots. So we'll go ahead and transpose this square root to the other side. Again, there's never a standard way, set way to do any equation solution. You just use good mathematics. So don't worry if you adopt a little bit different technique. Just make sure that what you're doing is legitimate mathematically. So we're going to go ahead and isolate this radical by removing this one to the right-hand side. And then I'm just going to write what we're going to do. We're going to square. So the squaring process will give us 3x plus 1. Again, we square the radical and it's gone. We don't have to write the square part. We know that accomplishes that quickly. And then we square the 2, get a 4. And then, of course, the product of these two terms times 2. So that's a 2 times a 2. So 4 square root x minus 1. And then, of course, squaring the x minus 1 radical just gives us x minus 1, or the argument. So that at least simplifies in the first step. So now let's go ahead and equivalently write the simplification. So the 4 and the negative 1, that's a 3. And then we have an x. And then we have the radical term. Now just remember, if the radical is multiplied by a number, you don't have to worry about that. You just square that too. It won't make any difficulty for us. So now if we look at this, we'll transpose the non-radical parts to the other side. So subtract x from both sides to get a 2x. And then, of course, subtract 3 from the 1 to get a negative 2. But, of course, we can factor the 2. That's just a 2 times an x minus 1. And then what's left on the right-hand side is the square root of x minus 1 times the 4. Now, again, if we have additional factors hanging out, we certainly can absorb them, because extra numbers aren't going to help us solve the equation. They're just going to make it more difficult. So we can divide both sides by 2. So the 2's absorb. So we get x minus 1 equals 2 times the square root of x minus 1. So, of course, if you don't like writing the square roots, I'm a big fan of fractional powers. If you want to write to the 1/2 power, that's fine too. Anything you choose to do is certainly fine if that's more comfortable. So now what we want to do is square again. I think the first time you go through this is the simplest process. Again, you can make adjustments as you move through. So now as we square, we get x squared, and then x times the negative 1 times 2, negative 2x, and square the 1 plus a 1. So the perfect square formula. And then as we square the other side, we get 2 squared, which is 4. And then, of course, the x minus 1. So now if you see, by squaring twice, we have rid ourselves of the two radicals, and now we have a quadratic, which we certainly understand. It's like the first lecture where we were clearing the denominators to create a linear equation. We know how to solve that. So think of this technique as being very similar to that. So now we have x squared minus 2x plus a 1 equals 4x minus 4. So now we can just collect everything on one side. So the x squared is the only quadratic term. And then, of course, subtracting 4x from negative 2x gives us a negative 6x. And then if we add 4 to both sides, we have 4 plus 1, which is a 5. So now we're, sometimes we don't even need the AC lemma because the equation is so simple. Of course, now 5, AC is just 5, but we can write 5 as what? Well, let me not put the parenthesis too soon. We'll just write this as negative 1 times a negative 5. And of course, the sum of those two numbers is the coefficient of the x term. So when it's easy, it's truly easy. But that's good. This is a very good method. So we have x minus 1, x minus 5 equals 0. And then, of course, we now use zero product. So zero product setting each to 0 will give us x equals 1 or x equals 5. Now, like I said before, we've squared twice, so maybe it would be a good idea to check, and these checks will be fairly simple. So we have x equals 1. So we look at the original equation. So again, we replace x with 1, so that gives us a 3 plus 1, which is a 4. And then, of course, we replace x with 1, so that's minus the square root of 0, and that clearly equals 2, since the square root of 4 is 2, and of course, the square root of 0 is 0. So that one works. So x equals 5. Again, this is a lot simpler, probably what happens a little bit more often than when we have the complicated fractions. Even though that's doable, it does take a little bit longer. So x equals 5. Again, we replace x with 5, so that's a 15 plus a 1, so that's the square root of 16. And then, of course, x equal 5 gives us 5 minus 1, which is a 4, so minus the square root of 4. But this is just 4 minus 2, which does equal 2, which is the right-hand side. So both of these work. They get a check, and so we do have two solutions. Now, again, in some cases, you can just look at the equation and figure out solutions, especially if the solutions are relatively simple. And that's fine. There's nothing wrong with intuition. I mean, when you study equations that have differentials, often you will guess a solution and then make adjustments to it because you know the properties of the functions with which you're dealing. So there's nothing wrong with guessing a solution, but in a college algebra class, the whole idea is to show the technique, because certainly if you consider the last problem, guessing that solution would have been a little bit more complicated, and you want to be able to provide an algorithm of your logical deduction, because these techniques are very important, especially as you continue in math. And then, of course, in your STEM classes in science, engineering, and whatever, even finance. So again, be sure to provide the algebraic justification for your work, even though you can sometimes stare at that equation long enough and figure out some solutions. What we want to make sure is that we get all of them, and this procedure will do that for us. Now, there are some interesting equations that have to do with quadratic form. So let's look at some of these. So this doesn't require any new technique. It just requires making a deduction about a pattern that we see. So let's look at the following. So we have 14x to the fourth minus, it's good to start with these because they're the easiest to recognize, minus 5x squared equals 0. So we're going to say solve. In this case, I'm just going to say solve in C. Now, the directions for your lecture notes say solve in the real numbers. So again, if your homework says just solve in the real numbers, do that. But I want you to see that you actually already know how to get all of the zeros for this particular equation. Now, there are formulas that you can create to solve these types of equations in quadratic form. I've actually written one, but it's a little advanced because you can create more complicated quadratics that have the same solutions but are very complex to solve, quadratics with imaginary coefficients. But what I had done is develop this for a partial fraction decomposition set up in Calculus 2. So sometimes a new formula can have really great results, but it's not so good for certain things. There might be other techniques that'll be a lot quicker. And this is the technique I want to show you. Notice, instead of quadratic in x, I'll just write this, we have quadratic in x squared. Quadratic in x squared. So we don't have to worry about making any changes. We'll just treat x squared as the non-squared term, and then x to the fourth, which is the square of x squared, as the squared term. And then we have the same types of coefficients. We have an a equal to 14, no difference, a equal 14, b equals -5, and c equals -1. So once we have that standard form, it doesn't matter. We just now have quadratic in x squared instead. So we don't have any new theory. We just treat the new equation in x squared and be done with it. So now what's nice about this, as you can tell, this will work with the AC lemma. And like I said before, if you're trying to figure out if the AC lemma works, you can always look at the discriminant, because if the discriminant is a perfect square, then you're going to get the AC lemma to work. So now AC equals 14 times the -1. So now we can think of factoring the 14 as 2 times 7 and then putting in the -1, so we get the -5. So we can just do -7, in this case, times the 2. And the sum of these two factors does give us -5. So that's a check. So now equivalently, we can rewrite the middle term, 14x to the fourth minus 7x squared plus 2x squared minus 1 equals 0. So this is where we're really back to just factoring quadratics. That is, working with quadratic equations. We didn't have to do anything new here. Let me adjust this just a little bit. There we go. So now let's go ahead and do the factorization here. We can extract here the 7x squared in each term. 7x squared, and then we're left with a 2x squared minus a 1. And then, of course, we have the same thing over here. So I'll just put a shadow 1 in front of it. So now we have 2x squared minus 1 times 7x squared plus 1. Now, of course, what you can do here, which we've done before, especially with the linear equations, is go ahead and factor the 2 here and factor the 7 here. So we have a 2x squared, and then, of course, divide the 1 by 1/2, or divide the 1 by 2 to get a 1/2. And then, of course, now we have a 7, factor the 7, we get x squared plus 1/7. And this equals 0. So now these are all very simple quadratics because they have no x term. So we've reduced this to something really simple, basically square root property. Now, if you like, you can just go ahead and factor the difference of squares or you can just set each factor to 0. Let's just go ahead and factor each of these just to get some practice on what we're going to do when we get to theory of equations. So now we're going to have what? X minus 1 over the square root of 2, if we take the square root of 1/2, and then x plus 1 over the square root of 2, just using the difference of two squares. And then, of course, the 7 and the 2 we'll just put as 14 out here. Just take it to the side. And then, of course, here we'll have the imaginary unit. So we'll have what? X minus 1. You can just go ahead and put the I up in the numerator because there's no real part. So root 7. And then x plus I root 7 equals 0. So the key here is that we know that when we take the square root of negative 1/7, we get the square root of 1/7, which is 1 over root 7 times I. So if you like, you could just move the I up in the numerator. So now if you set all these to 0, this will give us what? 1 over root 2, negative 1 over root 2. You don't have to worry about rationalizing these unless you're just asked to in the homework. But if not, don't worry about it. And then you have I over root 7, and then negative I over root 7. So this would constitute, these two would constitute just the real solutions, and then all four together would constitute all four solutions. So that's not really a surprise. When you have theory of equations, you've got a fourth degree polynomial. So you expect 4 zeros. But what's interesting here is that we don't get any repeated zeros. They're all distinct. That is, notice these are complex conjugates because this is a real polynomial. We learned that in our last lecture, and these are just what they are. They're like conjugates, so to speak. They're additive inverses of each other, but not in the same context as we have here. But what we see here is just a very straightforward manner with how we can use algebraic identities and the fact that we have the AC lemma. So now if you wanted to write all of the solutions, you could put them in brackets. Now, of course, if you're just asked for the reals, you just include the first two. But I just thought this would be a good example of where we could include all of the zeros, because I've already shown you how to deal with the square roots of negative numbers. So just remember, if you have an equation in quadratic form, then consider what the new quadratic form is. But what's so nice about this is that since it factored, and we had these very simple factors here, we were able to break it down into 4 linear terms. All of these are first degree in X. And so that's what we call a complete factorization. And this will be something that we'll be doing with theory of equations. So this will already give you a head start on what we'll be doing there. And hopefully by the time we get there, you'll already have a level of comfort with this kind of technique. So again, quadratic form. Let's look at another one. Let's see here. Here's one. This has a few more radicals in it. I think this might be an interesting one to look at. And let's see here. Yeah, we'll try one of those too. So here we'll say solve the equation. Now we've got 8 times x to the 2/3. So here's where we get some practice with some fractional exponents, minus 39 x to the 1/3 minus 5. Now you're thinking, when you've got this quadratic form, you could certainly get examples where it wouldn't factor, and maybe you'd have to use the discriminant and the quadratic formula. So don't be afraid of those kinds of problems. They will occur, and so you have to use the quadratic formula because maybe you're going to get complex zeros or irrational zeros, So again, don't forget that you always have that available. But now notice here, different from the last, if we think of this particular problem as being quadratic in x to the 1/3, when we square x to the 1/3, we get x to the 2/3. So well, this is kind of tailor-made. Don't we wish all the equations would come in this form, and all? But of course, if there was a 5 over here, we just move it over. So we have the standard form. So now notice this is quadratic in x to the 1/3. Again, all of these types of equations occur often in future courses, pre-cal, of course, as you review college algebra, and a lot in calculus and differential equations, PDEs, advanced calculus, differential geometry, all of these things, and like even finance. I mean, they're as you continue to work, you will see equations like this. And then, of course, you will learn in calculus how to do some approximation techniques when you are forced to have to deal with situations where the particular terms don't combine in advantageous ways. And we'll cover that when you get to calculus. So now notice, if you will, it might be advantageous to think of it like this. Let me just give you a little extra here. Let's just say we have x here times 8. So we have x to the 1/3 squared. So maybe you can see the quadratic form a little bit easier. Then we have minus 39 x to the 1/3. And I'll just put the 1 out there, even though I don't need that, minus 5 equals 0. So this is just a little extra, since you've got the 1/3 power as being the unsquared term, so to speak. So this is the first degree term when we think of just the plain old x coefficient, but in place of x, we have x to the 1/3, and then we bump up to the square of that. So we indeed have the quadratic in x to the 1/3. We have the constant term, the first degree term, and then the squared term, so to speak. So first degree squared. Now, if you like, A is 8, B is negative 39, and C is negative 5. So again, these particular equations are to help you with factoring, and so maybe not to beat you up so much with the quadratic formula when you're trying to learn about quadratic form. So now notice AC, you can see here we get a gift. We have 8 times a negative 5, which in this case is just a negative 40, but that gives us an easy way to write the negative 39. So we'll just say this is just negative 40 times a 1. And even though that's kind of a cheap factorization, it certainly gives us the negative 39 that we need when we add these two numbers. So that was easy. So now let's go ahead and write this out. So we'll have 8x to the 2/3. I'll go ahead and write it back the way we did now that you understand this. And then we'll have what? Minus 40 x to the 1/3. And now our just plain old 1 x to the 1/3 minus the 5. Okay? So now we'll do the same factorization, factor by grouping, which I think is better than memorizing a formula. So we factor the 8 times x to the 1/3. And that will leave you with a what? X to the 1/3 minus a 5, which is what we have right here. This just like the last problem. Very similar. So you don't necessarily have to make a substitution here. Substitutions are good when they actually help with the logic, but if you make a substitution, then it really does cloud the work, and then you've got to back substitute, and that is a complication that you don't need. Just go ahead and read the problem for what it is, and I think you'll find that to be very straightforward. And now, of course, the last step here is that just we have x to the 1/3 minus 5 times 8x to the 1/3 plus a 1 equals 0. So now we'll do the same thing we did before. This is just a leading coefficient of 1, but let's factor the 8 because it makes it a little bit simpler. So we have 8x to the 1/3 minus 5, and then x to the 1/3 plus 1/8. So when you factor the 8, there's no 8 in here, so you just simply divide by, multiply by 8/8, and then you take out the 8 in the numerator, and you're left with 1/8. So now we can use zero product. So it's amazing. We can't get away from zero product, quadratic form, linear equations, quadratic equations. All of this theory we use over and over. And so this course is really fundamental in getting those basic techniques down. And if you practice, you're going to find that your work as you continue in mathematics will get easier. And then, of course, when we start talking about other types of functions, we'll apply the same techniques. None of these will go away. And so you'll get even better at it. And when you get to pre-cal, you'll continue the same methods. And then, of course, when you get to calculus, you'll be using the same ideas with some new objects that you learn about. So now we can set each factor to 0. So if and only if we have x to the 1/3 equals 5, or x to the 1/3 equals negative 1/8. Now notice when we do the quadratic form, we're not squaring anything. We're not introducing extraneous zeros. So we really do get legitimate work. We just, now it is certainly possible that the third root, of some real number does equal 5. So we just cube to find it out. So cubing both sides, we just get 5 cubed, which is 125. So this is using the technique that we started with. How do we remove the 1/3? Well, we raise each side to the third power. So we get x equals 5 to the third, or 125. That is legitimate. And now, of course, here, we know that we can take cube roots of negative numbers, no problem. Square roots are more complicated, but odd nth roots are easy. So again, x equals negative 1/8 to the third power. And of course, 8 to the third power is 512. So that gives us negative 1 over 512, 64 times 8. Again, another power that we use quite a bit. And these are legitimate. So now we have solutions 125 and negative 1 over 512. So the key with the quadratic form is simply witnessing the pattern. And what you see with this, I like what the author has done here. They're still giving you the opportunity to work with factoring. That is, when you think about it, you're getting more practice with factoring, and now you're using the ideas that you know how to get rid of radicals by raising to an appropriate power of n, here 3. And then, of course, remembering the fact that cube roots are very user-friendly because the negatives don't pose a problem. So that's a much easier path. And again, we haven't introduced any extraneous zeros because we haven't come up to a situation where we've squared or done anything like that. So that's an interesting problem. Now, what we want to do, and again, as you have other forms that are quadratic, just factor everything and keep that new term present, just like here, our new term is x to the 1/3 or x squared. Or if you have a fraction, just maintain that fraction, zero product, and solve it. So there's no issue in difficulty. Now, thinking about fractions, I have an example here that I want to do. Again, because I think the quadratic form is the most complicated. Getting rid of radicals is easy, but the quadratic form, again, you got to remember everything. You got to remember the factoring, the quadratic formula if you need it, and recognizing the pattern. So here's an example. I mentioned it, and so I don't need to just leave it out. So let's look at this one. So we're going to say solve the equation. So here we've got, let's see, 1 divided by x plus 6 quantity squared equals 1 divided by x plus 6. The author's so nice with the parentheses, even though you don't really need them in the second case, plus a 12. So when you look at this, it's the same thing as we had before, but not as user-friendly. Notice what's interesting about this is that we have a square, a quadratic, where we're squaring 1 over x plus 6. So that replaces the x that we're used to. So in this case, we have quadratic in 1 over x plus 6. So there's nothing new about this. The first problem we had quadratic in x squared. The last problem we have quadratic in x to the 1/3, and now we have quadratic in 1 over x plus 6. Like I was saying earlier, like having quadratic in a fractional term. So to put this into standard form, we'll just say 1 over x plus 6, and I'll go ahead and write this with the square where we need it, and subtract this term. So minus 1 over x plus 6, and I'll just write the first power here, and then minus the 12 equals 0. So I think in these examples, they're trying to get you accustomed to factoring, but just realize that if the factoring didn't work, we would have to use the quadratic formula. But I think it's good for you to practice with this first, and then we'll kind of ease into the quadratic formula as you get more expertise and more confidence with this. So now when we look at this, we have what? A equals 1, B equals -1, and C equals to -12. So if we look at AC is just 1 times -12 or -12. But again, of course, we have a nice simple factorization. We can use a -4 and a 3. And that's really simple because the leading coefficient here is 1. So that'll work since the sum of -4 and 3 is indeed -1. So now this one, kind of a freebie. So we have 1 over x plus 6. Oh, and let me not put an extra parenthesis here. That's in the way. Creature of habit. -4. And then we have 1 over x plus 6 plus 3 equals 0. So again, we get our -12, we get the middle term, and then the first term. So this is like, if you want to just think in the old times, we had x minus 4 times x plus 3 equals 0. That would be if we just had plain old quadratic in x. But now we have quadratic in 1 over x plus 6, but there's no difference. We're good to go. We've got the linear factors, and we use 0 product. So we just set each of the factors to 0. So equivalently, 1 over x plus 6 equals 4, or 1 over x plus 6 equals -3. So now, what's nice with the equalities is that we can reciprocate each side to get the x in the numerator. We can do that with inequalities as long as we can control sign, and that'll be something we'll talk about later, but that's a much more complicated procedure. But just reciprocating, we get x plus 6 equals 1/4. And so let's subtract 6 from both sides. So we have 1/4. And let's just write the 6 with the denominator of 4. So that's minus 24 over 4. So x is just -23 over 4. For this side, we'll do the same thing, reciprocate. X plus 6 equals negative 1/3. So again, we'll subtract 6 from both sides, but now we'll write it with the denominator of 3. So this will be minus 18/3. So X is what? Negative 19/3. So what we're seeing here, though this equation looks very complicated, it's actually quite simple. So again, when you are working your problems in math or even another class, look for quadratic form. Again, you can always solve equations in quadratic form because you've got the theory to do it. And of course, if it doesn't factor, then you could use the quadratic formula and the discriminant. But I think the best way to start the process is to work it with the factoring to build your confidence. So now we can just write, again, the solutions: negative 23/4 and negative 19/3. And we are done with that. So again, quadratic form is actually very illuminating in the sense that it gives you a powerful technique to solve equations that seem maybe complicated. You don't want to expand anything because you want to preserve the form. So it's essential that when you start the problem that you write something like this, that you remind yourself that the equation is quadratic in this term. That's really important. So again, we have quadratic in 1/x plus 6. And then we just utilize the theory as we've done before. There's no need to call it something else. That is just an extra step that really takes you away from looking at the form that's very clear. And if you think about it this way, it's actually easier that you don't clutter the problem with more substitutions. Now, of course, when we do calculus and we learn about integration, there will be times when we make some substitutions that are required by the technique because we have no choice. But we only do it when it builds the level of technique in the problem. When we are forced to do it or when we need to do it, it makes more sense, not just adding extra steps when they're not necessary. Okay, now what I want to do is look at a couple of examples, and you're gonna look at these and think, well, this is not very difficult, because I just want to say something about factoring in general. For instance, if you have a problem that doesn't really fit maybe quadratic form, or there aren't any radicals in it that you have to contend with, and you're just looking at it to say, well, I need to solve this equation. Can I just apply basic factoring? And I want to look at a few of these, or just show you some examples. Solve the equation. Again, you will be forced to look at equations that don't have a particular form, but they have a nice factoring strategy. So let's look at the following. So we have 7x cubed equals 2x squared. And I've also got an example I want to show you with another radical. Now, when you look at this, you're like, oh, well, it's not quadratic in x. We just have two terms that have x's in them, and it looks very simple. So this is where you think, okay, what is the technique that we use all the time? We retire all of the terms to one side, factor, and then use zero product. So this is where we think zero product without attaching a particular form to the equation. We know this is degree 3 as like a polynomial, but it's very simple. So the first thing we do is we don't look to force any kind of form on it. We just retire everything, in this case, to the left-hand side. And then when you look at this, the first thing you can do, just to keep it simple, is to say that we have an x squared in each term, and then we'll factor the 7 just to keep it simple. So let's do this in 2 steps. So we have x squared times 7x minus 2 equals 0. And now, just to make it simple, let's just go ahead and factor the 7. So we have 7x squared times x, and of course, divide the 2 by 7 equals 0. So when you look at this particular example, you think, okay, 0 product, but notice, of course, you have the x that's repeated. So let's just go ahead and repeat that, or write it with a power. So, you can look at it like this: 7 times x minus 0 squared, x minus 2 over 7. So now I'll say more about that, and I'm just going to remind us of 0 product. So this is an example where if you just focus on retiring the terms to one side and clearing out the common factors, and then think about zeros. Notice here we've got x squared, but that's just disguised for x minus 0, and it occurs twice. So that has like a multiplicity of 2. And then, of course, we have the x minus 2/7 that occurs just once. And so by 0 product, even though this has multiplicity 2, it's just a repeated 0. We don't get 2 distinct zeros. We just get the 0 occurring twice. But when we write the solution set, we don't say 0, comma 0. That's redundant. But we keep in our minds that the equation does have 3 zeros. This is degree 3. It does have 3 zeros. It's just that the 0 occurs twice. So I'm trying to get you to think about multiplicity before we have to think about the theory of equations, to get you thinking about polynomials. So the 0 of 0 occurs 2 times, and of course the 0 of 2/7 occurs once. So we would say if and only if x equals 0 or x equals 2 over 7. And so now we have a solution set that looks like this. So when you think about factoring, again, this is where you have to look at the equation and think about the theory that we've used. And the 0 product is a big element of solving. I mean, this is something that you've been introduced basically when you started your algebra study in high school. And we will continue to use this over and over, because what we try to do is remove everything to one side and maintain all the structure of the equation, and then factor using basic techniques, and then apply the 0 product. So just remember, we didn't have to do anything challenging. For instance, we didn't have to look for an AC lemma or factorization. We didn't have to square or cube to remove radicals. We weren't looking for a complicated quadratic form. We simply were applying basic factoring techniques. So remember, there may be equations that are just quite simple. That is, basic factoring and 0 product will solve them. Now let's look at another one. This one will remind you of the AC lemma, but I don't want to let the cat out of the bag. So, well, I guess I just did. So solve the equation. It's interesting how when you take the calculus, you're just doing algebra and arithmetic over and over and over, to the point that you think, well, what is calculus? It's just a refined arithmetic. And by virtue of the fact that we have a good definition for a function, we can exploit that. So in calculus, you look at functions that have limits. You look at functions that have continuity, differentiability, and Riemann integrability. All these fancy words just mean that they have particular characteristics that allow you to do new operations. But all of these operations require you to do factoring and solving equations. So that's why we teach you all of these techniques before you get to calculus, because your mastery of these topics will make the calculus study very straightforward and very very interesting. It's always great to do a class in mathematics when you have the prerequisite knowledge, when you have confidence in the prerequisite knowledge. That's what undergirds you as you learn new ideas. So keep that in mind. Some of these topics may be fairly dry, but just remember the goal is to move into the calculus sequence so you can move on with your STEM education. Now, notice what's interesting about this particular equation. We've got 4 terms, it's degree 3, but we don't really have a situation where we can factor anything. I mean, they're all, as we would say, relatively prime. The only common positive integer divisor is just 1, and that's a constant term. So of course there's no x in here, and it's clearly not quadratic. So what we can do is factor by grouping. And that's where you just pair the first 2 and you pair the second 2. Now, of course, this doesn't always work. And when it doesn't work, we have to apply some other theory, which we'll talk about when we do theory of equations. But for now, we can simply use creative factoring. So we're going to have x cubed plus x squared. We're going to group those just like we do with the AC lemma. And here we're going to factor the negative 25 and just have an x plus 1. So basically here, I grouped these two and went ahead and factored the negative 25, and I just put these together. Since that was fairly clear that both of these terms have a negative 25, and then of course, I'll finish it off by factoring the x squared from these two. But again, we see that this works because we can look a little bit ahead and see that we're going to get another x plus 1 in this factorization. So x squared leaves behind x plus 1, negative 25, x plus 1. And so now factoring by grouping gives us x squared minus 25. So this is really simple, x plus 1. And then, of course, like we've done before, we can go ahead and factor the difference of 2 squares. So we have x minus 5. These are very common algebraic identities, and I want you to get comfortable with it because it'll certainly be quite a benefit in the future courses. I know I sound like a broken record, but when you spend the time on this work, the future classes will be much more enjoyable and not toil. I mean, you want your math classes to be enjoyable. So now, again, what's the buzz phrase? Zero product. So when we look at this, again, we did some creative factoring like we were doing the AC lemma, but we didn't start that way. And so now we can set each factor to 0. So we get x equals 5, or x equals negative 5, or x equals negative 1. Now, this doesn't mean that you can't just stare at the equation and figure out solutions. That's fine. I mean, if all you need to do is figure out one solution, then of course, if you knew polynomial long division, or synthetic division, you could reduce it and move forward. We're going to learn about those techniques. But the key here is that with the creative factoring, so to speak, we recover all of the zeros. So now we have 5, negative 5, and negative 1. Now, there's one last example that I want to cover before I finish the lecture, and it has to do with I believe, a quadratic form that's a little different. Not much. I mean, it's really simple, actually. You're going to think, well, I'm just repeating myself. But it showcases something that I think you'll find interesting. So we're going to say solve the equation. Now, of course, like I said before, if the problem stipulates that you solve the equation in a particular number system, then you do that. If they say find the real solutions, then that's what we do. Like I said before, you may uncover some imaginary solutions, but if the problem doesn't ask for those, then you do not include them in the solution set. But just practice the parts that you already understand, but adjust the solution set if you're working on homework. So we have something like this. I thought this was an interesting equation. And it certainly comes up quite a bit in mathematics. So when you look at this, and you think about this, this has quadratic form. That is, it's quadratic in the square root of x, because we could just think of x as the square of the square root of x. So if you wanted, we could, just to kind of add some extra notation, put the 2 here, the 1 here, and then of course transpose the 30, and of course it's fairly simple. This is a simple equation, but it has an interesting twist to it at the end. So we'll say quadratic in the square root of x. So what's interesting about this particular example is that, again, it does factor. Okay, you know, you at this point you can make up your own problems, and maybe they won't have nice factoring, and you'll have to use the quadratic formula as I've mentioned. But for now, we're sticking to the factoring mode, and we will introduce the other as your confidence builds. But notice here we have A equals 1, B equals 1, and C equals -30. But again, AC is just a -30. So now, of course, we just want the 1, so we'll keep up with the 6 and the -5. Again, a very simple factorization with simple numbers. Again, 30, -30 is just 6 times the -5. And of course, the sum of these two numbers gives us the 1. So that will work. We sometimes have to work a little bit harder, and we'll find situations when we have to do that. But if you can master this and again, do the combinations of the numbers, you will build your confidence as you work with the AC lemma. So now, of course, this first degree or leading coefficient's 1. So we get the square root of x minus 5, and we get the square root of x plus 6 equals 0. So again, 0 product. So equivalently, we have the square root of x equals 5, which is no problem, or we have the square root of x equals -6. And of course, when you look at this and you think about this, you're like, nah, this isn't going to work. This doesn't even have an imaginary 0, because the way we construct the complex numbers, we know they look at A like A plus BI. And so even if you assume that, you're not going to get a solution here. So this just has no solution. You know, no solution in C. I mean, it's like, you know, it's not that it doesn't have a real solution, it just doesn't have a solution. So I thought that was interesting when you think about this particular example, because when we think of, for instance, like if we thought, okay, there's a solution to this. Let's just think of it this. If we said that x was equal to some complex number. So for instance, we'll say x equals A plus BI, where A and the B are real, okay? And so if we square both sides, this gives us A plus BI equals, and of course, the square of -6 is 36. And so, of course, this implies that A equals 36 and B is 0, okay? But that's it. The square root of 36 does not equal -6. So even if we thought of x being complex in the sense that it has a real and imaginary part, it still doesn't work. So there is no solution here. So that, I thought that was interesting, and we haven't come up against that. And so when we think of expanding into the complex number system, there's still equations that don't have solutions. Of course, when we think about integer polynomials and the like, we've got an algebraically closed system that's really quite elegant. But here we're kind of stuck. So there's no solution there, even in the complex. But of course, here we can square both sides. X is 25, and that's completely legitimate. And notice here, this is only legitimate because this makes sense, even for real numbers. And so the only solution that we would have here is 25. So when you look at this kind of equation, what I think is interesting is this situation here. You get a very interesting interplay. Now, of course, you can talk about square roots of complex numbers. You can think about square roots of unity. There are all kinds of interesting ideas when it comes to complex arithmetic. And we've already thought about, conjugates, complex conjugates. Z times Z bar is the modulus squared, where we get A squared plus B squared. And we talked about dividing complex numbers, multiplying them. And so there's all kinds of beautiful arithmetic there. But I thought this was an interesting situation that you don't see very often. And don't just assume that there's a complex zero, because there isn't. Okay, so like I said before, practice with the imaginary unit, practice with the quadratic form, the radicals, and factoring, because these particular methods will be very useful as you continue your work in mathematics. So that's all I have to say for this, and we'll see you soon. Thank you.